Good evening and happy Wednesday. We finished looking at the limit, right? Now we're moving on to the derivative. Right. Let's actually change that. That should be fine. Let's say we have some function like that, f of x. Let's call this a. And let's say that's the point bf of b. Good enough. This line that passes through those 2 points it's called a secant line. And n, so slope of the secant line, right? Remember rise over run? So a line that touches the graph at a specific point it's called a tangent line. Right? And the idea of what we're doing is we're taking the secant line through the point AB, and we're just going to move the point B closer and closer and closer and closer to A. Now we're going to do the same thing on the other side, right? So we'll have another secant line. Right, we'll move that point closer and closer and closer to A, which is a limit. Slope of the tangent line. Would then be this limit. This is how we define a derivative. Right, so the derivative of f of x at A is just the slope of the line that is tangent to f of x at x equals A. Furthermore, we write f prime of x, right? So this is read f prime of x. We can also write it df dx and it's the limit as x approaches A, f of x minus f of A all over x minus A. Sorry. I'm not doing the derivative function just yet. It's f prime of A. I'll worry about the other notation later when we actually look at the derivative function. An alternative formula. Limit as h approaches 0, f of A plus h minus f of A all over h. You may also see instead of an h, a delta x. When dealing with derivative at a point, so the derivative, I'm just going to stick with this form. Now, if we're asked to find a tangent line, right? There are two common forms of a line. The most common. Recalls y equals mx plus b, called slope-intercept. Where m is the slope, b is the y-intercept, right? There's another commonly used form. Y minus y naught is equal to m times the quantity of x minus x naught. This is the point slope form. So when looking at a tangent line, start with point slope form. We'll have y minus f of a is equal to slope m, which is f prime of a, times x minus a. Right. Rearranging some terms. We'd be able to write it this way. Right. This is our equation of the tangent line. What we're going to do is go ahead and find an equation of the tangent line at the given point. Right, first thing first, let's go ahead and just find f of 3, right? Because we're going to need that. Nine, 18 plus 30, 48. Now we're going to go ahead and find f prime of 3, right? Because we need the slope. Limit. X approaches 3. F of x minus f of 3 all over x minus 3. Now you should notice that by its very definition, this formula for the derivative always gives indeterminate form if you do substitution. Right, so you always have to perform algebra. Go and factor out a 2 from the numerator. Right? We can factor the numerator, right? 8 and 3. Kidding me. Left with 2 times the limit of x plus 8. 2 times 11, 22. Tangent line would be 22x plus f of a, which is 48, minus three times f prime. And that's what, negative 16? So there's our tangent line. Okay. Let's first find f of 4. Four cubed. 2 to the 6th times 2 to the 7th. 128. Oh, oops. I forgot the plus 4 times 4. So then 128 plus 16. 38, 144. Right now f prime of 4. Limit as x approaches 4, f of x minus f of 4 all over x minus 4. And factor out of 2. Right? Very useful trick. Because as it stands right now, it does not look like we can do factor by grouping. $72, though, is 64 plus 8. No, not plus 8. Okay, so just put the group the minus 64 with the x cubed, right? Minus 8 within the 2x. Now let's factor. X cubed minus 64 is now a difference of cubes. From that second group, we can factor out a 2. Now there's an x minus 4 common. Left with x squared plus 4x plus 18. What was I looking at? No idea. X minus 4's cancel. We're left with x squared plus 4x plus 18. That limit 16 and 16 is 32. 32 and 18, 50. And look what I forgot. I forgot to carry that 2 through. So 2 times 50, 100.
I have a question. Two steps to go. Didn't you already cancel the x minus 4s? And then you brought it back? Am I missing something?
2 steps ago. Here or here?
That one, yeah. Didn't you cancel the x minus 4s there, and then to the next one?
I factored x minus 4 out.
Oh, yes, okay.
So that I could cancel. Right? Y is then equal to 100x, right? F prime times x plus f of a minus a times f prime of a. So we're looking at 144 minus 400. Which is minus 256.
When you factored that out, what happened to the original x minus 4?
What original x minus 4?
When you factored it out and then you just distributed the plus 2 to the 16 to make it plus 18.
Right.
One of the x minus 4s went away in the numerator, right?
Because we factored it out. Right. That's common term, isn't it?
Yeah. So do you just make it 1 in the numerator?
So just it comes out, right? So it's like it'd be like if I do 4x plus 8 and I factor out a 4, it's the same kind of concept. So what happened is once we factored out the x minus 4, what we were left with was this. right? Because I'm factoring an entire term out of both. Right, so you factor x minus 4 out of the first term, what are you left with? This x squared plus 4x plus 16. Factor x minus 4 out of the second term, you're just left with the 2.
Okay, thank you.
There it is. Oh, perfect. Updates. Nope, skip for now. Thank you. First, find f of 4. $17 quarters. Now we need slope. F prime of 4. Limit as x approaches 4. F of x minus f of 4. And then all over x minus 4. Now, we can also rewrite x inverse as 1 over x. Multiply numerator and denominator by a 4x. For x squared plus 4 minus 17 x all over 4x times x minus 4. Rearrange some terms. So I'm going to write that as minus 17x plus 4 instead. Just to make it standard. This time we can't factor anything out of the numerator. I could theoretically factor out a 1/4. I think I'm just going to leave it though. So we need to factor the numerator standard now. $16 plus 1 is 17. That means that it's going to factor as 4x minus 1 times x minus 4. And we're left with 4x minus 1 over 4x, which is what, 15 over 16? Fifteen over 16x plus 17/4 minus 15/4. Oh, that's easy. That's 2/4, which is a half. All right. F of negative 2. Just 1. That's nice. Limit as x approaches negative 2. F of x minus f of negative 2 all over x minus negative 2. Multiply numerator and denominator by x plus 3. We'll get negative x minus 2 in the numerator. Right? Okay. We can factor out a negative, can't we? Gives us -1. Right? Tangent line, -x plus f of a minus a times f prime of a. Our tangent line is -x minus 1. Yeah, all right, square root. Square root of 2 is f of -1, right? Now we need to rationalize. Numerator is going to become a difference of squares. Right, so it'll be the first term squared minus the second term squared. Denominator, gonna look ugly. X plus 1 times square root of 3x plus 5 plus square root of 2. And just so I don't have to write the denominator more than I have to, this is going to become (3x minus 3), right? Factor out the 3. Uh-oh. That's because that should be a plus 3, but I wrote minus 3. right? And we're left with this limit. Okay, what does that limit equal? Looks like 3 over 2 root 2. Contrary to what you may have been taught before, that answer is perfectly acceptable. If this were an algebra class, you'd have to rationalize that, right? Get rid of the square roots in the denominator. Yeah, we don't have to do that anymore. I don't think I want to either. I'm going to leave it like that. F of A was root 2 plus, or sorry, minus, right? A times F prime. So it's going to become plus and then 3 over 2 root 2. If we multiply the first term by 2 root 2, we're going to get 4. And then add 3. Seven over 2 root 2. And if you did decide to rationalize it, you're not wrong. That's what you would have. Right. You also wouldn't be incorrect if you decide to write this as a single fraction. Right, that would also be accepted. Okay, last bit. F of 4 is going to be 1 over root 9, right? So 1/3. One over square root of 2x plus 1 minus 1/3 all over x minus 4. I think this one gets really ugly. Multiply both numerator and denominator by 3 times the square root of 2x plus 1. That gets rid of the complex fractions. Now we're going to have to rationalize. Numerator becomes 9 minus the quantity of 2x plus 1, which is negative 2x minus 8. So now denominator is really ugly. What I can now do, just center that. No, I screwed something up, didn't I? 9. I did. Oh my, I'm not having a good day. It should be plus 8, not minus 8. And it's 9 minus 1. Here's the question. Do I want to factor out that 1/3 as well? I think I do. So I'm also going to factor out the 3 from the denominator and just have a negative 2/3 out in front. Then the x minus 4s cancel. This is the limit we're left with. It's going to be what? So this will be 3. That'll be 3. 18 in the denominator. So it's negative 2/3 times 1/18. Which is negative 1/27. One third and minus negative 4/27. That's what, 13/27? If there's our tangent line. Again, could write that as 13 minus x all over 27. That's fine. Any questions on those? I think there were 6 of them. Any questions on those 6 problems? Now, what if we said, okay, f of x is tangent. What's f prime of pi over 4? Well, to find it, you'd have to set up this limit, right? Oh boy, that's going to be a fun limit. That limit is 2. Of course, the question is, how would you get that to be 2? Well, it's a pain. This is why we want to find an easier way of calculating derivatives, right? Well, it would certainly be nice if we can find the derivative as a function, right? So some f prime of x, which would then allow us to plug in our x value. Right? So that is what we look at next, defining the derivative function. Okay, so the derivative function f prime of x equals limit as h approaches 0, f of x plus h minus f of x all over h. This is the derivative function. Domain is a set of all values x that make that limit exist. There are several ways to represent the derivative function. We have f prime of x. This is called the prime notation. We also have df dx. This is known as the Leibniz notation. We also have capital D subscript X, F. I refer to this as differential notation. As these two are written, they make no sense. These are what are referred to as operators. Right? They operate on something. Limit is also an operation. Right? If I just write this, that doesn't make any sense. Right? So these are known as the differential operator. Now, I want to be very, I want to make something clear. Technically speaking, this right is the derivative function. What we looked at previously is the derivative. The derivative is a scalar, right? It is, by definition, slope of the line tangent to the point, or tangent to the function at a point. It's typically referred to as the derivative at a point. Well, it is just a derivative. However, generally speaking, when we talk about derivatives, right, if you're asked to find a derivative, it's usually implying that you want the derivative function. So I follow that convention as well. Well, I'll say find the derivative when I really mean to say find the derivative function. Okay. So we're going to differentiate the following functions. We're using the definition first. Right? That means that we want to plug it into here. By the way, this function that I just boxed in green, does that look familiar? All right, so again, show of hands. Who recognizes that function? Uh-oh. Uh-oh, not a single hand. That either means no one recognizes it or no one's paying attention. This is the difference quotient, which was studied in pre-calculus. What that means is that for calculus, we just add one additional step, right? We take the difference quotient, which is pre-calculus, and we pass it through a limit. Calculus is easy. Algebra is difficult. I typically tackle these problems in a 4-step process. First step is to find f of x plus h. Right? And then simplify it as much as possible. Second step. Take what was just calculated subtract from it f of x. And again, simplify. 4 minus 4, 8x minus 8x, negative 5x squared minus negative 5x squared. Third step. Take what we just calculated and divide it by h. right? H over H. This one, we're left with 8 minus 10x minus 5h. That is all algebra. Finally, take what we just calculated and pass it through the limit as h approaches 0. That is our derivative function. Right? Let's look at this one. F of x plus h. First, we have to expand. Let's distribute that -2 through. There we go. Now take what we just found, subtract out f of x. I think this time I'm going to go ahead and factor out an h. Now, take the previous step. And divide it by h. And finally, take that and pass it through the limit as h goes to 0. That gives you your derivative function. Any questions so far? Okay. So here's what I want you to do. Ponder this function. Let's think about finding the derivative of this function using the definition. We will pick up right here when we come back at 7:50. So I will see you all then. And we're back. We'll continue on with finding derivative functions. First, we find f of x plus h. We 1 over the square root of x plus h. Really nothing more to be done. Let's now take that. Subtract out our f of x. Write it as a single fraction. All right. Now we take that. Divide out an h. I'm just going to rewrite it. Now we're going to need to rationalize this. Specifically, we're rationalizing the numerator. All right, x minus x, 0. Now we have h over h, which is 1. Now, finally, let's go ahead and pass it through the limit as h approaches 0. That should be negative 8, shouldn't it? Which means this would be negative 1. So we can write it either as 1 over 2x root x or 1 over 2x to the 3 halves. It should all be negatives. I kept dropping that negative. Don't know why. Okay. Find f of x plus h. Now subtract out from that f of x. Divide that by h. Now we're going to have to rationalize. Let's see what we get. 9 minus 9, negative x minus negative x. All right, we are left with this. C and h over h. And this is what we should get. Pass it through the limit as h goes to 0. Right, and this is what we get as our derivative. Okay, now we have a rational function. Right, so f of x plus h first. Yeah, might as well distribute it. Take that, subtract that f of x. Oh boy, here's the fun. Oh my, how did I end up? So crooked. And so common denominator first. Now we have to do a bunch of distributions. minus cubed plus 2x squared h minus 3x squared minus 2x minus 2h plus 3. So 2x cubed minus 2x cubed, negative 3x squared minus negative 3x squared, 3 minus 3. No, I was right. That should be plus. I'm missing a few terms. Just move those off to the side for now. Because I'm missing a minus 3h squared and then a minus 2x. That makes more sense now. Those minus 2x's will cancel out. All right, so we had a 4x squared h minus 2x squared h. That leaves with 2x squared h. We have minus 6xh plus 2xh squared minus 3h squared minus negative 2h. Factor out an h. Finally, almost done. Now all that's left to do is take that and pass it through the limit as h. No, I have to divide by h first. Not having a good night. Divide by h, so the h's cancel. Now, I'm at the limit. If they go to 0 in the numerator, we're going to have 2x squared minus 6x plus 2, and in the denominator, two x minus 3 squared as our derivative. Okay. Make this the last one of the definition. First, f of x plus h. Subtract out f of x. Divide out h. You don't have to rationalize. All right. Now we have to expand. All right, so expand out the numerator. X cubes go away. What we're left with has an h in common. And all simplification done, we're left with, oh, wait a minute. Really not having a good night. We just completely dropped the other term in the denominator. What we're left with is actually 3x squared plus 3xh plus h squared over x plus h to the 3/2 plus x to the 3/2. We can now pass that through a limit. We get 3x squared over 2x to the 3/2, which simplifies 3/2 x to the 1/2. Any questions before moving on? Okay. Now I can see how much of a pain this is to work with, right? So the definition is great for theory and seeing what a derivative actually is. But when it comes to calculating the derivative, it's not very practical. So what we do next, and then for the next 3 days, next 3 classes, is develop rules and techniques to find derivatives. Okay. We start with basic rules of differentiation. Right, there are a few of them. Where am I? So here are the basic differentiation rules. First, we have the constant rule. What it says is for any constant C, the derivative of C is 0. Power rule. For any real number n, the derivative of x to the n is n times x to the n minus 1. Scalar multiple rule. For any real number C, the derivative of C times f of x is equal to C times the derivative of f. Sum difference rule. If you take the derivative of the sum or difference of functions, then it is the sum or difference of the derivatives of the individual derivatives. Right, so derivative of f of x plus or minus g of x is the derivative of f of x plus or minus the derivative of g of x. I think that's all of them. That's all the basic ones. Just as a side, the last two, the scalar multiple and the sum difference, are called linearity properties. What that means is any operator that has these two properties, these two rules, is what's known as linear. So the differential is linear. If you have to take linear algebra, you're going to see this again. What we're going to do is now just use these rules to find the derivative of several functions. Right? F of x is 2 to the 40th. Well, that would mean that f prime is just 0, right? By the constant rule. Okay, so what about 7/4 x squared minus 3x plus 12? What the sum difference rule allows us to do is just go term by term. Right, so we're going to start with 7/4 x squared. Well, that's a scalar multiple. The scalar 7/4 times now the derivative of x squared, which is a power rule. Three x again is a scalar multiple, so it's going to be the scalar 3 times the derivative of x, which is just 1. Again, it's a power rule. It's x to the first power. And then plus the derivative of 12, which is just 0. Our derivative is 7/2 x minus 3. Again, we go term by term. We'll have 1.4 times the derivative of t to the 5th. By power rule, that's 5t to the 4th. Minus 2.5 times the derivative of t squared. By power rule, that's 2t. And then plus the derivative of 6.7. That's a constant. So the derivative of that is 0. 1.4 times 5 is 7. 2.5 times 2 is 5. Our derivative is 7t to the 4th minus 5t. Okay. Well, here we have a product. We don't have a rule in our toolbox yet to deal with a product of functions. Right? So that means what we have to do first is expand it out. Three u squared plus 5u minus 2. Now we can take its derivative. Three times the derivative of u squared by power rule 2u plus 5 times the derivative of u, which is 1, minus the derivative of 2. Our derivative is 6u plus 5. Again, right now, we do not have a way of finding this derivative in our toolbox. Right? It's a fraction. Specifically, the independent variable is located in the denominator. However, we can rewrite this. Right? Remember, we're allowed to bring things in the denominator up to the numerator if we raise it to the negative power. So we can write that as 5r to the minus 3. F prime now would be 5 times the derivative of r to the negative 3. Power rule. Bring the exponent down, negative 3. Right? Times r. Now subtract 1 from the exponent. Be negative 3 minus 1. Which is negative 4. Negative 15r to the minus 4. Right, and typically what we want to do is we want to write our answer in the form in which the question gave. Right, so since the function was given as 5 over r cubed, we should write that as negative 15 over r to the 4th. Fractional exponents. Power rule still works. Bring the exponent down. New exponent is the old one minus 1. So we're looking at 5/3 minus 1. Which is 2/3 what's going on? Somehow control got clicked. Oh. All right, again, bring down the power. Now 2/3 minus 1. Negative 1/3. There's our derivative. 5/3 x to the 2/3 minus 2/3 x to the negative 1/3. No need to simplify. So before we take this derivative, there's some preliminary work we have to do, right? First, we have to distribute that cube root of x through. Now we need to write this in terms of powers. Well, cube root of x is x to the 1/3 power. Right, we can then write this function as 2x to the 1/3 plus x to the 4/3. Which means that y prime would be 2 times now the derivative of x to the 1/3 power rule. Bring the power down, which is 1/3. X to the 3rd minus 1, which is negative 2/3. Plus, bring the 4/3 down. Then it is x to the 4/3 minus 1. Right? However, that's not how the problem was given to us. We need to write this back in terms of radicals. Two over 3 cube root of x squared plus 4/3 cube root of x. If we really wanted to, we could write this as a single fraction. It'd be what? 2 plus 4x all over 3 cube root of x squared. All right. S prime of R. Well, isn't 4 pi a constant? All right, so it'd be 4 pi times the derivative of R squared. Eight pi R. But we're again going to have to rewrite the function because we don't have a tool, or a toolkit for this yet. So first, write the radical as a rational exponent. Now we can divide each term in the numerator by x squared. So x to the half divided by x squared is going to give us x to the negative 3/2 plus x over x squared, x to the minus first. Now we can take the derivative. Bring the exponent down. Negative 3/2 minus 1. Bring the exponent down. That's negative 1 minus 1. So rewrite this. So what I'm going to do for this one, I think, is go ahead and factor out the smallest term, which is x to the minus 5/2. It's going to factor out a negative. And write this as a single fraction. And so we have negative 3 plus 2 root x all over 2 root x to the 5th, which we can also rewrite. if we wanted to, as 2x squared times the square root of x. Then we're going to have to rewrite this. Right, so first thing we notice is if we have the square root of a product, we can split that as the product of square roots. And then just write the square root as t to the 1/2. G prime of t. That square root of 5 is a constant. Bring the power down. Then it's t to the 1/2 minus 1. I don't know why I actually wrote out minus 1. That square root of 7 is a constant. Bring down the power. Then it is the power minus 1. How do I want to proceed here? Oh, I don't need to worry about writing as a single fraction because the problem didn't. Okay, perfect. So we write this as a 1/2 times the square root of 5 over t, and then minus root 7 over t squared. James being weird. Here we're told that A, B, and C are real numbers. Right, so they're just constants. Rewrite this. Right. Now we're able to take its derivative very easily. Right, A is a constant. Now derivative of z to the minus 2. Plus b times the derivative of z to the minus 1. Right, and then the derivative of c is 0. Factor out a negative z to the minus 3. What are we left with? 2a minus, or plus rather, b times z. Two a plus bz all over z cubed. Negative. Okay. We're going to have to rewrite this one as well. Okay. Right, 4 cubed 64, fully simplified. We can write this as 1/64 t to the minus 3 plus 1/4 t to the minus 1. Right, d prime, 1/64 times the derivative of t to the minus 3. Then plus 1/4 times the derivative of t to the minus 1. And now simplify. You can factor out a negative. Factor out a negative 1/64 t to the minus 4. Left with 3 plus 16t squared. All right. Derivative negative 3 plus 16t squared all over 64t to the 4th. Before we continue on, are there any questions? Okay. Well, if you look at this, the derivatives is a function, right? It's called the derivative function. So wouldn't it make sense that it would have a derivative? Right? But then that would be a function and it would have a derivative. But that's a function, so it's going to have a derivative, right? And so on, and so on, and so on. These are called higher order derivatives. So f double prime of t is called the second derivative. Why am I using t? I have no idea. Right? right? And the second derivative is just the derivative of the derivative. Right. Then we have the third derivative, f triple prime. And that is the derivative of the second derivative. Fourth derivative. All right, it's just the derivative of the third derivative. And so on and so on. Now I have to wait until this syncs. Now it's synced, perfect. And so for the final two problems, it wants us to compute the first four derivatives. So f prime. Power rule, 6x to the fifth. F double prime would be 6 times now the derivative of x to the fifth, all right? Because remember, the second derivative is the derivative of the first derivative. Triple prime, third derivative. Derivative of the second derivative. And finally, the fourth derivative would be the derivative of the third derivative. Right. First derivative is 6x to the fifth. Second is 30x to the fourth. Third is 120x cubed. And the fourth would be 360x squared. And then last one for the night. 1100. Well, 1100 is a constant, right? So its derivative is 0. What about the second derivative? Well, isn't 0 a constant? So once you hit 0, every subsequent derivative after that will also be 0. So all four derivatives in this case happen to be 0 because the original function was a constant. Any questions? Okay, so tomorrow evening, we're going to continue looking at the derivative by looking at three more rules: the product rule, the quotient rule, and the chain rule. Right? Obviously, the product gives us a way to find the derivative of a product of functions. Quotient rule is going to give us a way of finding the derivative of a quotient of functions. The chain rule gives us a way of finding the derivative of a composition of functions. Okay. So let's take a look. All right, so don't forget, you have 2 assignments due tonight. You have the first report, as well as assignment number 4. Third quiz will be due tomorrow before the start of class. Then on Friday, that's when the remaining assignments from tonight are going to be due. So the first reflection, as well as those 3 MyOpenMath assignments. Also, as a reminder, there will be no meetings next Wednesday and next Thursday. Everyone have a wonderful rest of your night. I will see you all again tomorrow evening at 6 p.m.
Thank you.